All right, so welcome back, and I hope you are all doing fine. So in the last class or in the last week, we've been talking about state machines, right? And that kind of culminates everything that we have learned so far. We're trying to put together everything that we have learned so far in the design of state machines. Okay. Now, as you already know by now, the state machine is it's a machine that you can design to exist in multiple states, right? So now, as with any design, we need to come up with a sequence of steps so that when you start following the sequence of steps, it makes it a lot more easier for you to not lose track of your design process. Okay, so what are the sequence of steps that you need to go through as you design a state machine? Okay, now first of all, you're given a problem statement. So we'll examine a problem statement in this example. Given a problem statement, what is the first thing I need to do? Right? Just like when we're designing combinational circuits, the way we designed it, with the way we followed through, was that we would come up with the what is called the level 0 design first. We identify the inputs, the outputs to the system, the relationship between the outputs and the inputs, translate that information into a truth table, and we basically use the K-map approach to obtain the function. Now, in the design of state machines, given a problem statement, the first thing that you would need to do is identify the states that machine would exist in. That's the critical step. How many states should the machine have? That's the first step. Okay. Now, let's say the state, the machine, you in the design analysis, you come up with the figure of 2 power n states. Okay, let's say you have 2 power n states uh, in your design. Okay, now that corresponds to how many state variables should you be having? That corresponds to n state variables. Again, if I have n states or 2 power n states, I don't need 2 power n state variables because each state has to be encoded with a unique binary code. For 2 power n states, I need only n state variables, right? My state information is encoded in the state variables. This is something that we have discussed in the last class. So identify the states. Identify your inputs, just like you have done before. Identify the inputs for this particular state machine and the outputs. Okay. Now, once you understand the problem statement, put the information down and as a snapshot, right? In terms of you basically obtain the corresponding state diagram for the system. So basically that gives you a snapshot of your entire system. So really where you're really applying your thinking process, where your creativity and all, these are the steps A, B, and C. Those are the most important steps in the design process of a state machine. Okay, because once you're through that steps, the next sequence of steps are basically you're applying some techniques, right? So more or less a mechanical process to realize the state machine. But this is where you really have to apply your creative process, thinking process. Okay. Once you obtain the state diagram, basically you translate that information as we have seen in the last class. Translate that information into a state table. Again, a state table is nothing different from a state diagram. They are basically equivalent. It's just that state table allows you to synthesize your state machine. Okay? And then through the state table, you realize your state machine. machine functions. Now, again, I go back and I stress the importance of the general block diagram of a state machine. This is something that we have considered in the last class. So basically, this ends up once you're through this A, B, and C steps. This ends up with basically designing this combinational block. The combinational block that takes in your present state variables. Let's say A, B, C. These are the present state variables. I don't have too much. Right? Let me see if I can fit them in. That's your inputs. Again, you can have multiple inputs for simplicity. I just include one, but you can have X, Y, Z, or more than that. That's your present state indicated by the variables A, B, and C. You can have multiple outputs, but for now I just indicate one of the output here. And then your next state. Again, remember that the way you calculate the next state, you consider the present state and the input acting on the present state to calculate what is the next state should be, right? And you move forward in time. Again, this is just an example where I considered 3 state variables, but you can have multiple, more number of the state variables than that. So that's your D flip-flops here. Again, for now, I'm looking at D flip-flop implementation of the state machines, but in general, you can use any flip-flop. You can use JK flip-flop as well to implement your state machine. So that's your DA, DB, DC. The number of flip-flops in your design should be equal to the number of state variables, right? And that should be equal to the number of flip-flops in your design, because each flip-flop will store one state variable. So that's your generalized design. And of course, because in the future, my future state becomes my present state, as we've discussed in the last class, then I have this feedback. So that's the general block diagram of a state machine. And this is something that you need to remember, because all the state machines will be having this kind of a setup. Okay. And ultimately, what it boils down to is the design of a simple combinational block. Once you're through these steps, you just have to design this combinational block, and that represents your level 0 diagram of your combinational block. That takes, you have identified the inputs. For the inputs of this combinational block are X and the present state variables A, B, and C. You have identified the outputs Y and the next state variable or the future state variables A plus, B plus, and C plus. Okay, which store what should be the next state, right? And from the state table, you obtain the truth table for this particular block, and from the truth table you implement your Y, A plus, B plus, and C plus. Okay, and the functions for Y, A plus, B plus, and C plus as a function of X, A, B, and C. Okay, and then you join, and then basically you realize the circuit, or realize your state machine by incorporating that particular circuit that you just calculated within this block. And that's it. That's the end of your design process. Okay. All right. Now, let's. So it's a good idea again to practice working on as many problems as possible, because it's a fun way. Designing state machines is actually a very fun design process, I would say. And because it challenges you, as you can see. In the last class, we have, again, just as an illustration, we implemented the state diagrams of a regular D flip-flop, of a JK flip-flop. What else did we do? Of a counter, right? And let's take a few more examples of implementation of state machines, state diagrams. Okay, because once you're through the state diagram step, the rest of the steps are more or less straightforward. Okay. All right. So let's do something more practical now. Let's say you're tasked to design a traffic light controller system. Okay, so now you have two roads. So that's the design problem. Okay, so you're an engineer working on something on this design process, and you're approached by a client. Okay, so you have two roads. So that's the problem statement. You have two roads. Let's say this is the main road. Basically, you have an intersection, and you want to design a traffic light controller for this intersection as a state machine. Okay, so you have a main road and the side road. Okay, and so what do you have? So basically, you have again a main road, side road. Okay, you have three signals for each, right? So you have main green, main red, main yellow. You have side green, side red, and side yellow, right? So those are the signals that we have at the intersection. Okay. Now, and what are the different combinations of the signals that we have, right? If my main signal is green at the intersection, what should be the side signal? So the main road, my main signal is green. Obviously, the side signal should be red, right? Should be red. Okay. If a main signal is yellow, side signal should still be red. Main signal is red, side signal should be red. Well, yeah, I mean, if from your experience, you see that there's a small fraction of time where you have once the signal transitions from yellow to red, you have all the intersection signals are at red for a small fraction of time before the other signal goes to green, right? Just for safety purposes. So incorporate that as well here. Okay, and then you have main. In this case, main is red. Side becomes red. Side becomes green. So now the side traffic can move on. Main red, side yellow. Okay, and that's it. So we have all the possible combinations. Now we have to design a traffic light controller system that stays on. Let's say you have a counter for each combination of these signals. My counter is on. My counter is on for 30 seconds, let's say. So it starts counting down from 30 seconds. Okay. And once the counter reaches 0, then the next sequence of switching happens. Next sequence of light signals should occur. Okay. So let's say my counter is indicated by time by input t. T equal to 0 implies that the counter is still counting. The count is not done yet, right? Counting down. The counting is not done yet. So you start from 30 seconds, 29, 28, and so on. It goes all the way down to 0. When t equals 1, that implies the count is done. When the count is done, then the next signals should the next sequence of signals should turn on. Now, let's try to design this. You're given this, you have this main red. Of course, you can always complicate the system. Let's say you have a different count for the main green, for the amount of time the main should be green, because that's the main road, versus amount of time the side should be green. So you can always complicate this problem to make it more intelligent, right? The signaling system can be made more intelligent by incorporating more sensors on that. So again, there is no limit to what you can do. But again, let's try to keep things simple at this time, and stick with the same amount of time the counter is on for the main green or side green for each signal transition. Okay. Now, how do I design this? What should I consider as states now? Let's say I want to design this as a state machine. What should I do now? Can I get some feedback from the class? How should I go about designing this? My client has provided this information to me. So all the information is put down there. And according to the client specifications, I need to digest this information, organize this information, and identify the states. In the sequence of steps, that was the first step, right? We need to identify the states, draw the state diagram corresponding to this particular machine, or in this case, that's a traffic light controller that you're trying to design, and implement that. Because once you're through that state diagram, 90% of the problem is done. Okay, so any ideas here from the class? What should be considered as a states in this case? Five states, okay. What are those states? What should I consider as my states here?
The combinations you have written down on the left side.
Okay, let's do that. Let's go with that. So 5 states, that means I have 3 state variables. How many inputs do I have? One input, right? I've identified my inputs as well. I have inputs equal t in this case. Now, as you suggested, I have 5 states, and each of this in the signal combination itself, in this example, I will consider that as a state of that particular state machine, which is a good suggestion. And now let's start putting together the state diagram. All right, so let me define my states. As this particular combination as S0 state, this particular combination as S1 state, S2 state, S3 state, S4 state. Okay. All right, and now let's put down the state diagram. I have S0 state. These are all the states. I put them down. S2, S3, S4. Okay. Now, again, I go down to each state, look at all possible combinations of the input, and for each input combination, I look at the state transitions. And then once I'm done with all the state transitions, I go to the next state, repeat the process. So it's an iterative process that I'll do for each state. So I go to S0 state. Now, I have 2 combinations, right? T equal to 0 implies the count is not done, it's still counting. T equals 1 implies the count is done. If T equal to 0, when I'm in the S0 state, what should be the state transition? Should I transition to a different state? Should I remain in the same state? I have only 2 different possibilities here because I only have one input. With one input, I only have 2 different possibilities, 0 or 1. Okay, remain in S0. That's correct because my count is not done. I should not be changing my signal. If T equal to 0, I remain in S0. With T equals 1, the count is done. If the count is done, then I need to transition to the next state, right? Main green, main yellow. The signal on main should be yellow, and the side should still be red. So transition. T equals 1, transition takes me to the S1 state. I'm done with S0 state, I move on to S1 state, do the same analysis on S1. Again, T equal to 0 when I'm in S1 state. That means I'm in this state, count is not done, I remain in the same state. When the count is done, I move on to the S2 state, which is main red and side red. Same thing on S2. T equal to 0 takes me back because the count is not done. The signals remain at the same values or the same colors. Count is done. I go to a main red and side green. I'm in S3 state, main red and side green. T equal to 0 takes me back to the same state. I don't change the colors. T equals 1 takes me to main red and side yellow. Okay. I'm in S4 state. That means my main is red and side is yellow. Now, with T equal to 0, I should remain in the same state. So that's kind of obvious. The count is not done. What about T equals 1? What should I do? After main red, side yellow, where should I be transitioning to? Should it be go to S2 or go to S2 is one answer. Main red, side red. So let's look at that combination. Because I have two different answers. It's okay. You can see it, right? T equal to 1. The other answer was go to S0. S0 is main green, side red. What do you think? Or should I be going to S2 or should I be going to S0? Let's hear. Garrett, what did you say? Let me see your chat. Okay. Why do you think you're wrong? Okay. S2. Okay. It has to go to both red. Okay. Okay. So let's fix on that. Because we need a state where both of them are red, right? Otherwise, it's kind of the motorist will be confused, and you want to avoid that for safety purposes. If it's an abrupt transition, then there may be some confusion there. So it's a good idea to have one state where main red and side red are there. Okay, so it looks like all of you agree. Yeah, that's a very good thought. It looks like most of you agree with this one, which is fine. It makes sense at the first instance, but we have a problem here. We are getting stuck in an infinite loop without ever going to my S0 state again or S1 state, right? Because if I have this transition, I start with this, go to S1, go to S2, I can go this, but then I will never be able to go to S0 state because there is no more transition there. I'm kind of stuck in this loop. That means my S0 state, which is main green, side red, never happens. So the motorists on the main road are stuck forever. Yeah, very good. Yes, we can. I would not say it's going to duplicate states, but we can assign another state as 5 with a similar configuration, which is perfectly fine. Main red and side red. It's just the out because this is just the output. This is just the output sequence, but I can have another additional state. I'm not really duplicating S2 back here. It's just an additional state, different from this S2. Okay, because this is this is actually a new state with the same output characteristics. So yeah, we don't want to do this. That will be too confusing. Or this will be not really good for the main road guys. So yes, I have another state as 5. Which outputs similar value, MR, SR. Okay. So T equals 1 takes me to S5 state. Again, T equal to 0 takes me back to the same state. T equals 1 finally takes me to S0 state. And now I have more of a complete picture. Now, now it's done. Does it make sense? That's a good catch. So that's how we design. it's you put down information, go through multiple iterations, okay, until you really find the right state diagram that actually conforms to the specifications, okay, to the specifications given by the client. All right, and then you start. Now, once you're done with this, the next of the steps are pretty standardized, right? You don't the thinking process is done. Next of the steps, you just have to follow a more of a routine process to design this. Okay, so that's good. So that's a good exercise. All right. If I were to design it, how do I design it? Now, so far, until this example, we really did not think too much about the outputs, right? What are these? These are really outputs, right? Somehow I need to send some outputs to my light sources, the green, yellow, and red light sources, so that they can switch in the correct sequence. So these are nothing but the outputs. So far, in our examples, we really did not pay too much attention to representing the outputs, right? So now let's actually talk about how do you represent the outputs in a state machine. Okay. All right. So let's do that. So we have this. Now, the way we represent the outputs, we can have two different ways of doing that. And the machine that you build based on how you represent the outputs are classified into two different types. Okay. You have what is called, so I can classify a state machine based on how you represent the outputs of the state machine into two types. So you can classify this as a Mealy type state machine, or you can classify this as a Moore type state machine. Now, what is a Mealy type? In a Mealy type state machine, the outputs are functions. In this case, the outputs are functions of the present state, okay, as well as the input acting on the state, on the present state. Let me be more precise here. Acting on the present state. So in this case, the output is a function of the present state as well as the input acting on the present state. For Moore type, the outputs are functions of the state itself, or the state only, of the present state only. Okay. What that means is, as long as I'm in a particular state, my output is determined by that state. Okay. My inputs, as long as I don't change my state transition, as long as I don't transition to a new state, my outputs don't change. Even if the inputs can change during the clock cycle, my output wouldn't change because my output is a function of the state itself. The present state I am in, my output is a function of that state itself only. That state only. Now, what do you think? You have two examples, two types of state machines. Which one of the state machine you think is synchronized with the clock? Or which one of the state machine you think is the output synchronized with the clock? The question is, the Mealy and Moore type. I've defined what those what makes a machine Mealy versus what makes a machine Moore based on how the outputs are represented. Which one of these state machines, the outputs are synchronized with the clock? What do you think? Let's see what the class thinks about it. Is it Mealy type or is it Moore? In which case, my outputs are synchronized with the clock. Remember, my inputs need not be synchronized with the clock. Inputs are what you're applying on the system. More, right? Because my states are synchronized with the clock. My states, which are held by the flip-flops, states or state information is held by the flip-flops, and the flip-flops itself and the flip-flops are synchronized with the clock. Because my outputs are functions of the state itself, my outputs are automatically synchronized with the clock. So these are, you can call these more of a synchronous state machines. In the Mealy type, on the other hand, because the outputs are functions of both the present state as well as the input. If the inputs change even before the next clock transition occurred, there is a possibility for the output to change, even though the next activate has still to occur. Okay, so in the Mealy type, I need to put an additional constraint on my inputs, saying that my inputs have to be synchronized with the clock to make my Mealy type synchronized with the clock. For the Moore type, I don't have to do that. I don't have to have that additional constraint. Okay. Now, in what way are they represented on a state diagram? Okay. So let's examine that. So the Mealy type and the Moore type. All right. So that's your Mealy type. That's your Moore type. And I will give you an example of a Mealy type state diagram, some random state diagram. Okay. And a Moore type. So let's say I take a simple example of one that has 4 states. Let me call it S0, S1, S2, S3. Because my outputs are synchronized, because my outputs are functions of the present state and the input, the way I represent my outputs, let's say my X is the input, let's say X equal to 0, takes me back to the same state, giving me an output Y equals 0. My outputs and inputs are clubbed together here. Whereas, let's say X equals 1, takes me to X1 state, giving me an output Y equals 1. So my outputs are functions of both the present state and the input. Likewise, you can finish this diagram. X equal to 0 produces Y equal to 0. X equals 1, Y equal to 0. Again, this is a random state diagram. I'm just writing down just to show how the outputs are represented in a Mealy type state machine. Okay. Let's say X equal to 0 takes me to S0 state, giving me an output Y equals 1. X equals 1 takes me to S3 state, giving me an output Y equals 0. And finally, we have X equal to 0, Y equal to 0, X equals 1, Y equals 0. Some arbitrary state diagram. Okay. But the important thing is, you should note how I represented the outputs along with the inputs. So that's how my Mealy state machines are specified as. For the Moore type, again, let's consider a state diagram that has 4 states. Now, if you recall, for a Moore type, my outputs are functions of this present state itself. Okay, it does not depend on the input. As long as I'm in a particular state, my output depends on that particular state itself. Okay. All right. So my outputs are represented along with the state information itself. So let's say, as long as I'm in a 0 state, I am fixing my output Y to be 0. Okay. S1 state, let's say my output is still 0. S2, my output is 1. S3, my output is 0. And again, I have the inputs acting on the states. Let's say X equal to 0 takes me to a 0 state. As long as I'm in the S0 state, my output is 0 because my state is clubbed. My output information is clubbed with the state itself. let's say x equals 1 takes me to one state with an output of y equals 0. X equal to 0 takes me back to S1 state. X equals 1, x equals 0, x equals 1. Oh, wait a minute. Let's have the state transition. X equals 1, and finally x equals 0, x equals 1. Okay. All right. So that's how you can distinguish between a Mealy type state machine and a Moore type state machine. Okay. So outputs are clubbed with the state itself. Outputs are functions of both the state and the input. Okay. With that said, now so far all the examples we have taken, right? These are some of the examples we have taken. We looked at the JK flip-flop. We implemented the JK flip-flop. The D flip-flop. We looked at the state diagram for all of these. We looked at the state diagram for, what else did we do as examples? JKD counter. And recently the traffic light controller. The way we draw those examples. How would you classify each of these as? Would you classify them as a Mealy type state machine that we just implemented, which we just shown, or a Moore type? Let's start with the traffic light controller because that's something fresh in your mind, right? We just did it. How would you classify the way we draw the state diagram? Would you classify as a Mealy type or the Moore type?
I would say it's more like a Moore because it depends on like main road is red. That's why it's side road is green or something like that.
Okay. Yes, it is a Moore, and the reason is the way I have defined my states itself. My states are the outputs, right? The way the outputs are switching, those are my states. So with each new clock transition, I'm getting to a new state with a new output. And as long as I'm in that particular state, my outputs are fixed. So that's why I would classify a traffic light controller system that we just draw as a Moore type. The counter, what about the counter? Again, the way we drew that. Remember a counter? Let's say a counter that counts up 0, 0, 0, 0, 0, 0, 1, so on, 1, 1, 1, 1, and goes back to 0, 0, 0, 0. How would I draw this as a state diagram? What would be a counter be classified as? A Moore type or a Mealy type? How would you draw the state diagram? Again, it depends on how you draw the state diagram, right? That's my values of the count. Is it a Mealy or a Moore? Mealy, okay. So let's draw the state diagram for a counter and let's then decide on that. What would I choose as my states for a counter? For a counter, what are my states? Any ideas here? Each value, okay. So 0, 0, 0, 0. Let me call that a 0 state. Each value itself is a state. It's one state. So how many states would I have then in total? I would have 16 states, right? For a counter, I have 16 states. Implies how many state variables? Because each state has to be encoded with a unique code. I have 4 state variables, right? 4, perfect. Now let's draw the state diagram for that. So that's good. S0, S1 is true, and so on is 15. And if I want to draw this, that would look something like this. I don't have an explicit input here. I don't have to worry about input. It just has to, with each clock transition, it automatically enters a new state, right? I don't have to worry about the state transitions here. S0, S1, S2, so on, S50, S15, back to S0. I transition through all of these states. With each new clock transition, I'm automatically transitioning to each state. Now, as long as I'm in a particular state, right, for example, S0, as long as I'm in this particular state, the count value has to be preserved, right? The count of 0, 0, 0, because that's how I associated S0 as the state with a count of 0, 0, 0, 0. As long as I'm in this state, the count value is preserved. On the next clock transition, I move on to the next state. As long as I'm in this state, my count of 0, 0, 0, 1 is preserved. That's my output. Again, remember, these are the outputs I want to see, right? And so on. As long as I'm in this state, 0, 0, 1, 0 has to be preserved. Okay. Now what do you think? Would that be classified as a Mealy type or a Moore type? My outputs are functions of the state itself, right? That's a Moore type. Very good. My outputs does not depend on the inputs. In this example, I don't have an input. It just has to transition to each new state with each new clock pulse. The way we have implemented JK flip-flop, again, the way we have looked at the state diagram for the JK flip-flop, the states, we based it on the output, right? You have Q equal to 0, Q equal to 1 state. So what do you think? For a JK flip-flop or a T flip-flop, the same thing we have done. How would you classify these as? Would that be a Mealy type or a Moore type? For a JK flip-flop, recall the way we've done it. I had an S0 state which coincided with the Q equal to 0 state. Okay. All right. S1 state which coincided with Q equals to 1 state, right? And then we had, if I have JK both equal to 0, when I'm in this state, I remain in the same state. With J equal to 0, K equals to 1, that's the reset state. I remain in the same state. I'm sorry, J and K are both inputs. J equal to 1, K equal to 0, I transition to the next state. And finally, J equal to 1, K equal to 1, when I'm in this state, Q equal to 0, transition to the next state, which is the toggle state. Right? So that was, I'm done with S0. And then we had the same thing here. That's the memory state with J equal to 0, K equal to 0, J equals to 1, J equal to 0, K equals 1 takes me to the reset state. J equal to 1, K equal to 0 takes me back to the same state. That's the set state. And finally, the toggle state. J equals 1, K equals 1 takes me to the toggle state. If I'm in this state, with this input acting, I'll go to the next state. Okay. Let me just take this off so there's no confusion here. Okay, now based on this, now that the state diagram is here, what do you think? Is that a Mealy or a Moore? As long as I'm in a 0 state, because the way we have designed our machine, I looked at the output of this this machine itself as the state, right? I associated S0 as a state where my Q equal to 0. I associated S1 as a state where my Q equals 1 for that particular flip-flop. So as long as I'm in S0 state, Q equal to 0. As long as I'm in S1 state, Q equals 1. Even if some input changes before the next clock transition occurred, I'm going to still remain in the same state until the next clock transition occurs. Right? So, what is it? Mealy or Moore? It's Moore. It's a Moore. Because for Moore, my outputs are synchronized with the clock. My outputs are functions of the state itself. And I can only transition to a new state. My output can only change only with on the next clock transition, on the next active edge of the clock, because my state transitions does not happen until the next active edge. I have to be sitting in the same with the same output as long as I'm in that particular state. So it's very important that you identify, looking at the state diagrams and how the outputs are coupled with the state, or the outputs are functions of both state and inputs. You should be able to make the distinction between if the state machine is a Mealy type or a Moore type. Of course, so all the examples we have taken so far in the class, these were all Moore type examples. So I think so now we should be able to actually take some examples that illustrate how Mealy types behave, right? Okay, so let's do that. So for that, let's actually take a design example, the design of what is called a sequence detector. Okay, and what we will do now is we'll implement a sequence detector both as a Mealy type and a Moore type. So let me give you a brief background on what a sequence detector is all about. Okay. Now, especially when you're working with, serial data, right? Serial data. Let's say you're trying to download something, you're trying to stream something. My information is being sent as packets, right? Instead of having all the information sent at once to be downloaded, we basically send one bit at a time, and then you stream that information at the receiving end, right? So now you have this communication channel, all right? Then I am sending these data packets. Let's say I'm working with 4-bit data. That means my each data packet is 4 bits long, right? I'm sending the information out. Now, the problem is, if I just look at the information, it looks something like this. I have 1 1 0 0 0 1 1 0 0 1 1. It's a stream of pulses that are going out along the communication channel. Now, how do I make sure where is my start of my packet, where is the end of my packet, right? I need to have some kind of a way to determine where is the start of the sequence or the packet, where is the end of the packet, right? Otherwise, it's all zeros and ones just going in. Then if I don't classify them in the right way, the complete information gets messed up, right? If this is the actual information packet, if I start classifying them as, with this, let's say, a single offset, the meaning of the information is completely lost, right? So I need to have some kind of a way to determine the beginning of a sequence, the end of a sequence. And one way of doing that is with every beginning, I put some code, let's say, that indicates that, that's the beginning of a sequence. Of course, that's a 3-bit code, but, I can have a sufficiently long code, a unique code that tells the receiver that, hey, this is the beginning of the sequence. So after the code, whatever you get, that's the data packet. And then you have another code, let's say, that would signify the end of a sequence. Okay, just as an example of example application of where sequence detectors can be used. All right. So what I'm trying to do now is, you have a bit sequence that is coming along, all right? So my X, let's say 0, 0, 1, 0, 1, 1, 0, 0, and so on. So you have a continuous stream of bits coming one bit at a time to your serial device. And what you want to do now is to identify a particular sequence along those bits. Okay. Let's say the sequence I want to detect is 0, 1, 0. This is the sequence I want to detect, as a simple example. Okay. So every time I detect the sequence in my input stream, my output should be, I should make the circuit output a value of 1. Okay. Now, there are two possibilities here again. My input may be something like this, 0, 1, 0, 1, 0. Now, this is a sequence, 0, 1, 0 is being identified. But again, I have an overlapped sequence as well here, 0, 1, 0. So I need to specify, when I'm trying to design the circuit, the client has to specify, overlapping sequences, are they allowed or are they not allowed? If they're not allowed, then that means I don't have another sequence unless I have 0, 1, 0 here, which case this is another sequence. But I cannot identify this if the overlapping sequences are not allowed, then this particular sequence is not recognized. Okay. If overlapping is allowed, then of course, this is a sequence, this is another sequence, and so on. So I need to specify in my problem statement if overlapping is allowed or not allowed. For example, in this case, let's say overlapping is allowed, or overlapped sequences are allowed. So that means my output should be something like this. Now, this is an instance where I've detected my sequence. So I have not detected a sequence until this time. Here I have identified a sequence, so my output should be a 1. Then no sequence, no sequence, no sequence, no sequence, no sequence. Again, here I've identified another sequence, so here the output should be a 1. Okay. No sequence, no sequence. Again, here I have identified a sequence, my output is a 1, and so on. So if X is my given input, then I should get an output Y, which is a 1 every time I have identified the sequence in my input stream. Now let's go about designing this as a state machine. So we need to design this both. So let's design this as a state machine using the principles of the state machine. We'll design this both as a Mealy type in the first instance and a Moore type. Okay. So let's start with the Mealy type first. Okay. Now, again, the first step in the design process is how to identify the states, right? So I need to identify the states. How should I assign my states? What do I mean by states of this machine in this instance, right? So let me go about this way. Let me say my S0, let's say start with S0. I'll call this the reset state, and you'll see what I mean by this. I call this the reset state. Okay. So every time I don't identify a sequence, I need to go to the reset state, stay in the reset state, and then move on to the next transitions based on the input stream. So this will be becoming more evident once we actually start drawing the state diagram. For now, okay. Now the sequence I want to identify is this 0, 1, 0. And this is the sequence I have to identify. I'm tasked with identifying. That means I need to identify 0 first, as the first bit, in the sequence. I need to remember that a 0 has occurred, and then I need to identify if a 1 occurs after that. That means I need to identify that a 0, 1 has occurred, and finally this entire sequence has occurred. Okay. So what I will do is I will assign S1 as a state that has identified that the first 0 has occurred. That has identified that a 0, the first 0 in the sequence, has been identified or occurred. ID'd. All right. S2 as a state that has identified that a 0, 1 has occurred in the input stream. And let's see if we can get by with 3 states. Okay, so now you know what you need to do, what the output should be. Let me see if I can put together a state diagram for this particular state machine that can identify a 0, 1, 0 sequence as a Mealy type. So I'm trying to draw a state diagram for a state machine as a Mealy type state machine. Start with 0, S0. Okay. Since I'm drawing it as a Mealy type, I'm not including the outputs along with the state. My outputs depend on both the present state as well as the present input. Okay. So I'm in the S0 state, which is the reset state. Let's say the first input is x equal to 0. I'm in this state, an input of x equal to 0 occurs. Okay. What should be the state transition? Should I remain in the same state? Should I transition to a new state? What do you think? I've designated my states as S0 as a reset state. Transition, very good. I need to transition to the S1 state because I designated S1 state as a state that has identified that a 0 has occurred in the input stream. Okay, so S1, x equal to 0 takes me to S1 state and giving me an output. What is the output? Let's say y is the output. What should be the output? Should it be a 1 or a 0? 0, right? Because I have not identified the entire sequence, so that should still be a 0. All right. Now, again, remember that I need to look at all possible combinations. Yeah, that should be a 0, right? Because I should output a 1 only when I've identified the entire sequence. Okay. I'm in S0 state. The other possibility is x equal to 1 possibility, right? Now, when I'm in the reset state, and x equal to 1 occurs, let's say. I'm trying to look at my input stream. I'm in the reset state, x equal to 1 occurs. Should I remain in the same state? Should I transition to a different state? What do you think? X equals 1, yeah, that's correct. If an input of x equal to 1 occurs, when I'm in the 0 same state, right? Because 1, if it's something like this, I have my input, I got 1. Again, 1 is not the first bit of my sequence. So I ignore this, or in other words, I remain in the same state, I ignore that, and start looking for the next bit. Let's say the next bit is 0. Now I know, okay, this could be a part of my sequence. So I go to S1 state as a state that remembers that a 0 has occurred. Does that make sense, Eric? In other words, if I'm in the reset state, if x equals 1 occurs, because 1 is not the starting of my sequence. I remain in the same state and start looking at the next sequence, next bit in the sequence. Okay. So I'm done with the S0 state. Okay, because I looked at all combinations of the inputs, and of course, what is the output? I have not identified any sequence. Output is still 0. Now I'm in the S1 state now. That means 0 has already been identified. The first 0 in the sequence has been identified. Now, if a 0 occurs, should I remain in the same state? When I'm in S1 state, the next bit is a 0. Or if my x is 0, transition to S0 state. That's one thing. One answer was, should I transition to S0 state, or in other words, should I reset? Or the other answer was, should I remain in the same state with x equal to 0? Something like this. That's my input stream.
I would say reset.
Okay. So if x equal to 0 occurs, that took me to S0 state, right? Do you agree? X equal to 0 took me to S0 state. Now, another 0 occurs. Okay. Should I reset or should I go to, sorry, this is S1 state, right? S1 state. X equal to 0 took me to S1 state. Another 0 occurs when I'm in the S1 state. Should I reset? When I reset, that means I ignore that and I start counting for the next bit. Or the other possibility is, hey, this could be the start of another sequence, right? Because if I have something like this, then I need to know that this has occurred. And the state that indicates that this has occurred is S1 state, right? Do you see what I'm trying to say here? Get it? So should I transition? Should I remain in the same state now? Same state, right? Because then this next 0 could be the first 0 of my sequence. So I would ignore this, start looking at this as a potential starting of my sequence. So I remain in the same state. So I should not be transitioning. I would remain in the same state. So x equal to 0 took me to this state. Another 0 takes me back to the same state because I start counting this 0 as the start of my next, as the potential beginning of my sequence. Okay. All right. So and then of course, no output. I have not identified the output yet. So there is no output here. And what else? Now, x equal to 1. When I'm in S1 state, a state that has identified that a 0 has occurred. And now, what about the transition for x equal to 1 condition? If I'm in S1 state, an input of x equal to 1 occurs now. How should I transition?
X1, Y1, maybe? X1, Y1.
No, what is my state though? Next state. Let's talk about the next state now. What should be my state transition?
Right.
State transition, right? Transition to S2. Why? Because when I'm in this state and x equal to 0, x equal to 1 occurs, that means a 0, 1 has occurred in my input stream. And the state that is designated as a state that has recognized 0, 1 is the S2 state. So now I need to transition to S2 state with x equals 1. I need to transition to S2 state because I have identified 0, 1. 0, 1 in my input stream. What should be my output? Did I identify the entire sequence? No, right? I have not identified the entire sequence, so my output is still 0. Okay, So I'm done with S1 state. I looked at these two possibilities. Now I'm in S2 state. If x equal to 0 occurs now, again, a good idea would be to go through the sequence transitions in this way. So 0, 1 took me to S2 state, and now a 0 occurs. Again, remember that in this case, overlapping sequences are allowed. Okay, now 0 occurs now. Which state should I go to now? S1. Perfect. Why? Because this particular 0 could be the start of a next sequence, right? So that's why I would go to S1. This could be the start of a next sequence, something like that. So that's why I would count that as the first 0 for the next sequence. That means I need to go to S1 state with x equal to 0. What about my y? Y is a 1, right? Because I have identified the sequence. 0, 0, 1, 0. So my y is a 1 because I've identified the entire sequence. Okay. Now I'm in S2 state. 0, 1 took me to S2 state, and a 1 occurs. Now, when I'm in S2 state, what should be my state transition now? Should I remain in the same state? Should I move to a new state? What should that state be if I have to move to the new state? So basically, in the input stream, I get something like 0, 1, 1, right? And 0, 1, 1 is not a sequence. 1 is not the beginning of any sequence, so I reset and start looking for the next sequence, right? So if 1 occurs when I'm in S2 state, I transition to S0 with an output y equal to 0 because I have not identified, this is not a sequence. I have not identified any sequence. I transition to S0 state. Okay? Does it make sense? Now you can follow through. You can follow through your yeah. To the state diagram. Okay. So let's say my input stream is x equal to 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, and so on. Okay. And you transition through your state diagram with these inputs and see if the state diagram actually makes sense. Now I have 0 as S0 state. 0 takes me to S1. 0 takes me to S1. Then 1 takes me to S2. And then 1 takes me back to S0 state. So that's my state transitions are something like this. S0, S1, S0. Right? Now 0 takes me to S1. 1 takes me to wait a minute, is that right? S0. Oh, sorry. 0 takes me to S1. This 1 took me to S2. Another 1 takes me to S0. Right. Next 0 takes me to S1. 1 takes me to S2. 0 took me to S0. And I've identified a sequence. Is it right? No, S1, sorry. 0 took me to S1 from S2. And I've identified a sequence here. So you can run through this sequence and see if your state diagram actually conforms to how it's supposed to be. Okay. Again, I'm in S1. Another 0 occurs. I still remain in S1. 1 takes me to S2. 0 takes me to S1. Producing another 1. Again, same thing. S2, S1, and so on. So this makes sense. This actually works. right? So I can run through this sequence, any sequence of my input, run through this state diagram to make sure that it's working according to expectations. All right. Now, how should I go from here? So now the next part of the problem is actually straightforward. This is the part where you actually have to think through. Next part, you basically follow the protocol. So you create a table between the present state, your input, the next state, the output. That's the format for your table. How many state variables should I have? I have 3 states. Number of state variables? 2. That's correct. Right? So I can code it as 0, 0, or assign a unique code of 0, 0 for S0 state, 0, 1 for S1, 1, 0 for S2. So that's, since I have 2 state variables, let me call them A and B. Let me call my input X. Next state is represented as A plus and B plus. Output represented as 1. Now it's a matter of designing your block diagram, right? This combinational block that takes in the input X, takes in the present state information A and B, giving you an output Y, and the next state A plus and B plus, going through this D flip-flop. We call it DA, DB, QA, QB. That's your clock. And you're designing this combinational block. You're looking for A plus, B plus, and F and Y as a function of X, A, and B. That's it. Right? So you basically put down the information 0, 0, 0, as if you're designing a combinational circuit. You look at all possible combinations of the input. But in this case, the input for the combinational block is A, B, and X. So on 1, 1, 1. Put down the information from the state diagram, right? For when I'm in a 0, 0, 0, A and B corresponding to 0, 0 corresponds to a 0 state. With an input of X equal to 0, took me to S1 state, which is encoded as 0, 1, with an output of Y equal to 0. Likewise, 0, 0, 1 took me to the same state, which is 0, 0, encoded as 0, 0, output of 0, Y equal to 0, and so on. Okay. And then you can do this, and then you can populate this table. Remember that I don't have a state that is encoded as 1, 1, right? That means for these combinations, that corresponds to don't cares, right? Because those combinations are not going to occur. So for those combinations, it's going to be don't cares. All right, let me stop here. We'll continue this in the next class. But we have already seen an example like this before. So I'm hoping that you should be able to take it from here and finish the problem. But in the next class, we'll do it anyway. Okay. And we'll also implement in the next class the Moore version of this machine. How can I implement this as a Moore machine? We'll do that in the next class. Okay. With that, let's end this session here.